Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Lauri Siltala with us today. And I apologize for butchering that name. So just to get it on record, how do you say your name?
Lauri Siltala.
There you go.
Yeah, I'm used to it being
I did a terrible job.
Foreigners, so.
My apologies. So, Lauri, where are you at?
I'm at my home in the town of Jokela, about close to Helsinki in Finland, around 40 minutes by train. So not quite in Helsinki, but in the area, basically.
Yeah. Okay. Very cool. Very good. So we have, excuse me, a little frog in the throat this morning. So we have equinox coming up. Are things starting to warm up a little bit in that part of the world?
Oh yes, they are. We
Cool.
still have some snow left, but it's melting really fast right now, so not for much longer, I think, and it really is starting to get warmer.
Okay.
I went skiing with my brother last week, but I think that was the last time because there's not enough snow anymore at this point.
So are our winters ending earlier? Let's put it that way.
Generally speaking, yes, but it's been quite surprisingly long this year.
Okay. Were you born and raised in Finland?
Yes, I was.
Okay. So
born in Helsinki. So
you're a native. Okay.
Yes.
Very cool. Very cool. Awesome. It's one of my going to Finland remains on my bit bucket of things to do in life. Maybe I'll even catch the aurora there, which is something I still haven't seen.
I could also call back to a previous video from this series a bit, since you interviewed Grigori Fedorets this December.
Oh yeah.
And he was in Helsinki as well. And you asked him if there was any snow around here, and there wasn't at the time, but we basically got snow a few days after your interview with him, and now it's about to melt away.
Very good. Cool. That's right. Yeah, I did do that one. We'll put a link in the description below the video to that video as well. So you're number 2 on Finland. It's great. So Lauri, what do you like to do for research?
Well, I'm a PhD student. I'm working on computing asteroid masses and orbits and applying MCMC to the problem where everyone has traditionally used least squares methods for it. Also, as a little advertisement, I'm hoping to complete my PhD this fall, and I'm looking for postdocs. So if someone who's listening has one to offer, you should contact me later on.
Absolutely. Definitely. Well, congratulations on being very close to finishing.
Thanks.
That's awesome. Very cool. Because I was going to ask you where you are in your trajectory. So very cool. We'll put a postdoc plug out for you. Very good. And that is going to take us to this really lovely APJ letter on the mass and density of asteroid 16, Psyche. And Lauri, take us away.
Yeah, so we did a study on the asteroid Psyche for several reasons. First is that we had a previous mass estimation study with the latest version of our algorithm. I think it came out last year, which had Psyche as one of the objects we were studying. And Psyche was curious in the sense that while our method performed very well, for Psyche in particular, we got much lower mass estimates than expected, which of course also meant lower density estimates than expected.
Right.
And this Psyche is the target of an upcoming space mission. It's an object of great interest right now, and because of that and our interesting results last time, we wanted to study Psyche in greater detail in this paper.
Okay. So
in our previous study, okay, maybe I should shortly explain how this works first.
Okay.
So with this approach for asteroid mass estimation, we are looking at a massive asteroid, which I call the perturber, and some smaller test asteroids that are assumed massless that the perturbing asteroid has close encounters with. And during those encounters, the perturbing asteroid will perturb the orbits of the smaller test asteroids. And to estimate an asteroid's mass, you just model the asteroid's those perturbations of the asteroid by computing orbits for both the perturbing and the test asteroid and the perturbing asteroid's mass and fitting them into astrometry over a long time span.
Okay.
So you can use more than one test asteroid at the same time, of course. It has the advantage that you get more data, and more data should, of course, lead to better results. Now, in our previous paper, we did 2 separate mass estimates for Psyche with 2 test asteroids each. And in this bigger study, we used a total of 10 to get as much data as possible in. You could use more than 10 as well, but we are starting to reach problems with computational complexity as we add more and more asteroids in, means more data, more dimensions in the model, and so on. And CPU time is a serious concern, and those are the main reasons why we only have 10 here.
Yeah, only. So for each of those perturbers, do you do that as a restricted 3-body problem, or do you do it as an n-body problem? Or neither?
Yeah, it's definitely an n-body problem. It's
body. Okay.
With asteroid dynamics, it's really not feasible to just use 3 bodies, especially over longer time spans. So we are using all of the planets, but the gravity of all the planets, and also I think the 5 most massive asteroids in the gravity model here. So it's n-body.
Okay, good, thank you. Okay,
but
slide. So you're going to do an MCMC.
Yeah, the introduction has some of the stuff that I was also talking about. I could also mention that some of the background, the reasoning for the space mission that I've been talking about, it's that, like the paper mentions there, Psyche is thought to have a relatively high density, and both because of that and observations of its surface from radar and spectra, I think, indicate that the surface looks kind of metallic, and so many suspect that Psyche as a whole might be metallic as well, and
yes,
it could be something like the exposed iron core of a former protoplanet, and possibly a very interesting object, might even be the only one of its kind in the solar system. And people want to learn more about it, of course, and that's the reasoning for the space mission.
Cool.
And the asteroid's density is one of the very few ways we have of characterizing an asteroid's composition and structure with Earth-based observations, which is where this study basically comes in.
Very nice. Okay. So we talked a little bit about that. We got the test asteroid on the perturber. Okay, you're going to use a metropolis, and at some point we're going to slide down to equation 1 and figure 1.
Yeah, that figure 1 also comes back to our previous study that I was talking about with some tests, with some results for Psyche. In that study, that figure is basically directly from there. In that study, we demonstrated that our method allows us to integrate asteroid orbits into the future and get ephemeris predictions for that, basically from each accepted proposal of the MCMC chain. And so we can basically see how an asteroid is predicted to behave depending on, for example, Psyche's orbit or Psyche's mass, and kind of see the impact of the perturbations Psyche will have on the asteroid in the future. So that figure was such a prediction for one of the test asteroids we used, 151878, and what you can see here is the possible difference in right ascension allowed for this particular asteroid over time in what was the future from when that paper was made. Now the start is in the past already. And
what is what is the orange line and the blue dots?
Yeah, I'll get to that in a moment.
Okay.
But so the left-right axis has the difference in right ascension in arc seconds relative to the maximum likelihood, or relative to the right ascension prediction corresponding to the maximum likelihood MCMC solution, and the darker gray area represents basically the area predicted by the 1 sigma uncertainties.
Right.
Area predicted by the 1 sigma uncertainties of the MCMC chain, and the lighter gray is the 3 sigma area. So the right ascension should fall into those limits. And since that paper showed that there can be a particularly significant difference in possible right ascensions for this test asteroid around MJD 58,600 something. You can see that there's a range of like 2 possible arc second differences right there. And for that purpose, we took observations of Psyche with the Nordic, not Psyche, the test asteroid in question, with the Nordic Optical Telescope in La Palma, and the data points for those observations are the blue dots there, and the orange lines are basically the astrometric uncertainties of those observations.
Got it. Cool.
And and the red line there represents the asteroid's distance from Earth as a function of time, while the green areas were the areas where the asteroid is observable with some criteria that I cannot remember off the top of my head.
It's okay.
But that's basically the idea. We made a prediction before and added our observations on top of it to see where they ended up. Some other asteroid surveys also ended up observing this asteroid at the same time, and we are using that data as well. But we basically did observations of our own just to make sure that some will exist at that point.
Yes. Okay. Very good. Good.
I think that more or less explains that particular figure.
And here are your 10 asteroids, your 10 test asteroids. Got it.
Yes. They're all mentioned there. And as the paper mentions, all of those test asteroids have been those close encounters have been identified by other authors previously, and also may be used in practice. So they are not new in that sense.
Right. Okay. Then we get into Ceres and Vesta.
Yeah, they were here because some other planetary science authors have often asked me if we have ever tried this algorithm with asteroids that already have very well-known masses, since there are some significant uncertainties usually involved. But Ceres and Vesta have masses from the Dawn mission that are precise enough that we can basically say in this context that their uncertainties are 0. So we have direct ground truth values to compare our algorithm to in those 2 cases, and that's why they are included here. It's impossible to do anything nearly as good as Dawn with Earth-based observations like this. So it's not scientifically interesting, but it basically helps to make sure that we are getting realistic results for those asteroids.
Right. Very good. Okay. Yeah, we got some probability distributions for those 2, as a matter of fact.
Yes. So there in figure 2, we have results for the mass of Ceres in left and Vesta to the right, where the upper x-axis is the most interesting one, since it's mass relative to the Dawn value, and the dashed lines are the 1 sigma uncertainties, while the solid black vertical line is basically corresponds to 0.1, or the Dawn mass.
Yes.
So for Ceres, we see that the Dawn value is within our 1 sigma uncertainties, and for Vesta it's within 2 sigma, and I think that's all right. And if you look at the lower x-axis mass in absolute terms, we are indeed getting quite close. And personally, I'm fairly happy with those results. That unit is solar masses, just for the record, by the way.
Yes.
And
Yeah.
I could also say that those results only use 2 test asteroids each, and we would definitely get even better results if we added more, since more data again means better results. It was just a quick test, basically.
Okay. All right. Very good. And then we got same technique, but now applied to Psyche.
Yes, that sums up our results for Psyche pretty nice, where we have the mass again on the lower x-axis, but this time the densities, the masses correspond to on the upper. Of course, there's some uncertainty in the volume as well, which naturally plays part in the density, and that figure does not take the uncertainty of the density into account at all. So you have to keep it in mind, but this is basically dominated by the uncertainty of the mass anyway, so it's not a big deal in that sense. But yeah, that figure shows that the maximum likelihood value for the density of Psyche is 3.8 something, and but when you look at the 3 sigma probability, you can even get as high as 4.2 or so, or below 3.6, below 3.5 maybe.
Right. Okay. Sure.
That I think that basically sums up the entire interesting part of the paper.
Okay. And you've got some discussion here about other authors' results.
Yes, there's some comparisons to Bayer and Chesley, for example. They got we are getting slightly lower masses than them, but not by much. And so in comparison to our own previous paper, which I mentioned before, we are now getting results much more line with other studies. So I think it was our previous results were a statistical outlier in that sense, but they also had high uncertainties. And when you look at the uncertainties, this new result is within their possible range as well. So it's not completely wrong in that sense.
Okay.
But yeah, that also notes that Bayer and Chesley had slightly lower uncertainties than we did, even though we used much more data than them. There's some possible reasons for that, but there's some differences in data treatment for one, which definitely explains the higher uncertainties, in my opinion. But for some more context, in the field of asteroid masses, it's often thought that most estimates in the literature have unrealistically low uncertainty estimates, actually, which can be seen by when you're looking at different studies and seeing that they are reporting masses for single asteroids that completely contradict one another when you look at the uncertainties. And we are actively trying to combat that by using realistic algorithms and data treatment schemes. And in my opinion, it's working well so far in our previous studies as well. But so basically, it may sound like higher uncertainties are bad, but I'd say that they are just more realistic than previous studies.
Okay. All right. And then we got a whomping figure here. What is this one? These are your residuals for each of your asteroids. Okay, got it.
Yes, in right ascension and declination for each asteroid. There's a lot of data points, so it's very difficult to make out individual asteroids in there, individual observations in there. But yeah, you see the residuals for right ascension and declination for each observation as a function of time, where the black error bars are basically the 1 sigma range of the residuals themselves. When you look at all the accepted MCMC proposals, it's the 1 sigma area of where around the 33% or so best proposals have residuals at, if that makes sense, while the lighter gray areas are the assumed astrometric weights for each observation.
Okay.
And of course, the red vertical lines represent the periods of time where each given asteroid has had close encounters with Psyche.
Okay. Mm-hmm. Yes.
So there's not much of interest in there, but in my opinion, it shows that there's no big alarming problems with strange systematic errors or anything like that, and they are nicely lined up around the value 0 arcseconds as they should be.
Mm-hmm. Mm-hmm. Yes.
It's there just to show people that there's nothing really crazy going on in there. And that figure 5 is basically the same except with a longer time span for one of the asteroids, because that particular asteroid had a close encounter with Psyche a very long time ago, as you can see that in there in comparison to the others. So we added it in a separate figure because it would have seriously messed up the X scale of the other asteroids in that figure above.
Right. Okay. Very cool. Very cool.
Mm-hmm.
Okay. So would your measurements then support Psyche being a metallic core?
Yeah, so the paper discusses the possible physical implications of this density a bit. So many people say that Psyche could be an iron core, like I mentioned, and the one thing we can do with this density is comparing them to bulk density estimates of meteorites found on Earth. And to me, it would make sense if Psyche was really a metallic asteroid, then iron meteorites found on Earth should have a similar density to Psyche. And now those iron meteorites tend to have a density of around 8, so it's about 2 times what we get. And based on that, it seems very difficult for Psyche to indeed be an iron core, as some people say.
It's fluffy iron. Okay.
It's not. I'm not saying it's completely impossible, because it's possible that there will be some huge macro porosity, like big cracks and empty void areas in Psyche, that could explain a lower bulk density while it still could be metallic. But I personally have a difficult time believing it could be that porous, but I'm not saying it's impossible outright.
Right, fluffy iron.
But you definitely have to keep the macro porosity in mind. There could be cracks like that in Psyche, which could explain a lower bulk density in comparison to meteorites.
Cool.
But I'm not the first one to note that the density seems way too low to explain for Psyche to be a purely metallic asteroid. So, for example, Viikinkoski's paper, which I refer to there, suggests that it could be the parent body of, for example, some stony iron meteorites found on Earth, like the so-called mesosiderites. And those in turn had a density of, I think it was like 4.2 on average. And when you look at our 3 sigma uncertainties, our bulk density estimates still allows for that. So it seems very unlikely, but not impossible for that to be the case.
Okay.
And
very good.
Then there's the other recent suggestion of ferrovolcanism, where the idea is that around its formation, Psyche could have had a molten iron core, and some of that material could have been pushed into the surface through iron volcanoes. So basically metallic lava that would have solidified on the surface, and that would basically explain a metallic surface, while Psyche would still have a mantle of stone, which would explain both the observations of a metallic surface and also a lower density. So it's, to me at least, it's a very attractive hypothesis. But
okay, sure.
So it's kind of
metal-coated key.
But overall, it's kind of a theory that's hypothetically predicted that it could exist in the solar system, not necessarily only in Psyche, but possibly in other places as well. But it has not yet been seen in practice, so it's very much hypothetical at the moment in that sense.
Cool.
It looks very attractive and interesting to me, but we don't know for sure if it's actually happening just yet. There was actually
presumably that's what the mission will partly tell us. Yes,
definitely. I'm very much excited to see what they will find out, what Psyche actually will turn out to be like. Even if it's not an iron core like the mission designers said it would be, I think it's going to be interesting to see what we find out regardless.
It will be interesting to find out what we got. Absolutely.
Yes.
So where do you think we go over the next couple of years with this? Are there new calculations to be done with maybe 20 perturbers? Are there's some laboratory astrophysics experiments that could be done? Just where do you think we go until Psyche gets there and sort of tells us?
Well, we definitely have people investigating ferrovolcanism, not me. I'm more focused on masses than compositions. So like only just like a week ago, there was a new paper in Nature Communications that had done some large-scale experimentation of ferrovolcanism on Earth, creating artificial iron lava basically, and seeing what it looks like when it solidifies. Its physical properties, things like that. So we have an idea on what to look for if we want to check if Psyche is indeed ferrovolcanic, things like that. It was a very interesting study as well. But otherwise, as for the mass, there are actually not that many people working on asteroid mass estimation. So I'm not completely sure if we'll get better results by then. But one thing is the Gaia mission that has had its second data release come out a while ago. The third is on the way, and that paper the paper we were talking about did not use Gaia astrometry, but it can be included in mass estimation as well, and it's said to be one of the science goals for solar system astrometry from Gaia, because it's got very high precision astrometry. So of course, very high precision astrometry should also lead to better results, and it can be used in that sense. Right now I'm working on a new paper that does combine Gaia Dia2 data with Earth-based astrometry for asteroid mass estimation. It's not just focused on Psyche, it's a bigger general thing, but that's definitely one thing that I'm pretty sure is going to help Psyche mass estimates as well sooner or later, the Gaia data. Now, there's the second Dia2 release still has some weaknesses, since there's something over 10,000 asteroids in there. It sounds like a lot, maybe, but in fact, many interesting test asteroids for Psyche or other asteroids in general are not yet included in there. So we are not going to see the full impact of Gaia until maybe starting with the third release.
Yes. Okay. Very cool.
But overall, I can mention that for the Gaia paper we are currently working on, I'm seeing significantly lower residuals in both right ascension and declination in my test cases in comparison to the official Gaia Dia2 papers. So the Gaia data might be even better than the official Dia2 paper says, and that was fun to see.
Cool. There's spilling of a little research project for somebody looking for a postdoc.
Yes.
Very good. Lauri, I want to thank you so much for walking us through your really lovely APJ.
You're welcome. It was my pleasure.
All right. And thank you, everyone. And we will see you on the next one. Bye-bye.
Bye-bye.